Welcome back to this online tutorial. We are going to discuss about residue theorems. So we are going to first define what a residue is. Definition of a residue. So a residue. This is the coefficient. This is the coefficient a -1. You can also call it a1. Yes, a1. I'm just choosing a -1. There is no logic there. For should I call it for consistency? Yes, I'm just choosing that. It's the coefficient a -1 of 1 over z minus z naught in the principal part. Coefficient a -1 of the principal part of the Laurent series representation of complex function f of z. Recall that we said that, let us recall this. We said that the Laurent series representation of f of z about z equals z naught is given by about a point of singularity. It's given by f of z equals summation from k equals -infinity up to +infinity ak z minus z naught power k. So we said that we can write this as summation from k equals 0 up to infinity ak z minus z naught power k, then plus summation k equals 1 up to infinity a negative k then minus z naught power negative k. Power negative k. Still, I can write this as this function as f of z. If we substitute k equals 0 and naught, k equals 1 and 1, z minus z naught, k equals 2, in that order. Still here, substitute k equals 1, we shall get plus a -1 over z minus z naught power 1. This is a negative, so it goes down. Then plus a -2 over plus. So in some books, by the way, this thing these coefficients a -1, they are denoted as b1, b2. Yeah. So what is a residue? A residue is the coefficient of 1 over z minus z naught. The coefficient of this term here. In simple terms, a -1 is a residue. So by definition, a residue is the coefficient n negative 1 of this term here. We are going to take examples using what? Using the series representations which we obtained in the first tutorial. So kindly, if you did not watch that tutorial, review, because you cannot understand this minus the other things, because they are important. So recall that we expanded f of z equals 1 over z minus n1. 1 over z minus 1. We expanded that. Part A was about, we expanded it about 0 less than absolute z less than 1. So we got our answer as f of z equals negative 1 over z, minus 1 minus z minus z squared minus. So that is the Lorentz series expansion about z equals 0 of this function, considering that domain. So that thing is valid for that domain. So when you look at this Lorentz series representation of f valid in that given domain, if we are to identify the principal part, remember we said that this thing here with the fractions is the principal part. In simple terms, this is the principal part, starting from here going this side. Then the other thing is the analytic part. So for this thing, for this function here, we shall call this is the analytic part or the regular part, and this is the principal part. Yes. So the principal part, it's not a must that in all cases we shall get the principal part with finite number of terms. Because when you consider this general case, it's like the principal part and the analytic part should be infinite in nature. No, they shouldn't necessarily be infinite in nature. It just depends on the given domain. So according to this domain which was given, we obtain this as our Lorentz series representation, whereby now the principal part has finite number of terms, but the analytic part, the terms are infinite. You can see that we are heading to z to the 3, z to the 4. They are continuing in that way, yes. But there is no way we can obtain negative 1 over z squared, no. We only have this term representing the principal part. So if I want to get the residue in this case, the residue is equal to coefficient of 1 over. It's the coefficient of 1 over. So we obtain the series representation about z equals 0 for this function. You are seeing we are having absolute z minus 0. There's a silent 0. So we obtain this thing about z equals 0. And it's like here I'm having z minus 1 over z, then minus 0. Also here minus 0. Yeah, that's the general form. So if I'm to obtain the coefficient of 1 over z minus 0, that coefficient is negative 1. Yes, the coefficient is negative 1. So for this case, the residue is negative 1. Then we also had part B. Let us see what part B. We obtained what we obtained in that situation. Part B. Part B, we are getting this series representation about absolute z greater than 1. And our answer was f of z equals 1 over z squared plus 1 over z to the 3 plus 1 over z to the 4. So you can see in this example, you can see that this is our Lorentz, the general form of the Lorentz series representation of a function, of a complex function. So when you look at this, we are only having terms whereby z is now the denominator. We don't have situations where z where we are not dividing by z. It's like we don't have the analytic part for this example. The analytic part is 0 for this series representation considering the domain. So the principal part now has infinite number of terms. Analytic part is 0. So if we want to obtain the residue of this, the residue is the coefficient of 1 over z. Coefficient of 1 over z minus z naught. For this case, z naught is 0. So we look out for the coefficient of 1 over z. But we don't have 1 over z. That term is not here. So the residue is simply 0. The residue is 0. It's like 1 over z is multiplied with a 0. So that is the residue for that case. Part C, we are obtaining the expansion of f of z. I'm using the series representations which we obtained in the first tutorial. Part C, we obtained the series representation of f of z about what was the domain? About 0 less than absolute z minus 1 less than 1. So our answer was f of z equals 1 over z minus 1 plus z minus 1 minus z minus 1 square plus. So the residue, we want the residue. So this series representation was obtained about z equals 1. Yes, it was obtained about a singular point z equals 1. So we look out for the coefficient of 1 over z minus 1. 1 over z minus 1. The coefficient. So 1 over z minus 1 is this term. Its coefficient is 1. Its coefficient is 1. That is the residue. Then part D, we are obtaining the series representation of that thing about absolute z minus 1 greater than 1, I think. Yeah. Our answer was f of z is equal to 1 over z minus 1 square minus 1 over z minus 1 to the 3 then plus 1 over z minus 1 to the 4 minus. That was our series representation. That one was also obtained about z equals 1. So you just look at the coefficient of you look at the coefficient of 1 over z minus 1. We don't have 1 over z minus 1 here. You are seeing that we are starting with 1 over z minus 1 square. So the residue in this case, the residue is 0. So what have we done in this lesson? We have computed the residues of a function. We have computed the residues of a function, this one, considering Lorentz series representation valid within this domain, also considering the Lorentz series representation of f of z valid within this domain, within that domain, and within that last domain. So we can use the series representation of a function, the Lorentz series representation of a function, to obtain a residue. Now, what happens if at all we are not given these regions of validity? What shall we do? That is an important question which I'm going to answer in the next tutorial. Thank you for watching, and kindly subscribe to the channel. Yeah, we shall discuss.